So another concept that's closely related to surface tension is interfacial tension, and that affects what we call wettability. That is the amount a liquid wets a surface, a solid surface. So one way to think of surface tension is you can think of it as being essentially defined by the amount of energy that is required to increase the area of the interface between the liquid and the gas. And so that's what this formula is saying here, that the amount of energy required to increase a liquid-gas interface is related proportional to the surface tension of that interface. And since you can see that in general, increasing the amount of interface area is going to increase the amount of energy required, that anything that in the absence of other forces, anything that only has one interface is going to minimize that interfacial area, so it reduces the energy as much as possible. So that's why bubbles are spherical. So an air bubble in water or a soap bubble in air, those both take on the shape that has the smallest interfacial area between the air and the liquid. And that smallest area for any given volume is always a sphere. So that's why you see spherical bubbles. Interfacial tension is the energy required, just like surface tension, to increase the area of an interface for any kind of material. So not just gases and liquids, but gas and liquid interfaces, liquid to liquid interfaces, or liquid to solid interfaces. So surface tension is really just a specific word for liquid gas interfacial tension. So that concept is particularly important when dealing with droplets on solid surfaces. So if you look at this diagram up here, we have a droplet sitting on a solid surface surrounded by air. The liquid is sitting in a kind of a almost spherical shape. And compare that to this other droplet, which is really spread out on the surface and is kind of wetting the surface more. So that's two types of behavior that you see liquids have when they touch a solid. And we're going to characterize that based on this angle you see here between the angle at which the liquid touches and comes into contact with the solid. And so if that theta here is greater than pi over 2, that means the liquid is in somewhat of a spherical shape, and so it's really not wetting the surface. That's a hydrophobic surface. The liquid is, or in case of water, hydrophobic, but the liquid is not spreading out onto the surface. In this case, theta is less than pi over 2. Pi over 2, of course, would be straight up and down. And so this surface is wetting the surface. And so that's a theta of less than pi over 2, means that surface is wetting it. It's a wettable surface. So the things we need to do that, from a mathematical point of view, we need the interfacial tension between the air and the liquid, which is really just the surface tension. And that doesn't depend strongly on the gas. So we saw this with viscosity too. Because gases have molecules that are widely spaced, mostly the liquid isn't interacting with those molecules very much. And so we see that the surface tension does not depend very strongly on what type of gas it is. In fact, the surface tension in the vacuum is pretty much the same as that is in the gas, unless you get to very high pressures. It does depend strongly on temperature, because that affects how strongly the liquid molecules are attracted to each other. And we know that because we know if we raise the temperature highly enough, those liquid molecules will actually boil, because their intermolecular bonds will just fly apart and it'll become a gas. So we know it's strongly dependent on temperature, but the surface tension does not depend very much on what gas it is. So if you find surface tension measured in air, you're fine. The surface tension for air and solid is the other one you need, because the solid is in contact with the air here, and the surface tension for the liquid and the solid, which would be right here, where the liquid is touching the solid, or right here. So those are the three interfacial tensions that you need. And you can put those together in this formula from thermodynamics, the amount of work required to increase the interfacial area between the solid and the liquid. So this would be dA/SL, and this would be SL, and this would be SL. It's going to take work to increase that interfacial tension that depends on the interfacial tension of the liquid-solid interface. But you're going to decrease the air-solid interface. So you're going to subtract that surface tension energy. But then you're also going to increase the amount of liquid-air interface that there is. And that depends by geometrically on this formula here with the cosine. And I'm not going to prove that, but that is the formula that tells you how much increase there's going to be in the liquid-air interface as you increase that solid-liquid interface. So as this droplet is spreading out, the amount of solid-liquid interface is increasing, but also the amount of air-liquid interface is increasing. At equilibrium, that dWdA will go to 0. As the work tries to minimize itself. So you get to dWdA equals 0. That's the equilibrium condition. So you either have to put work in or get work out to change from there. And that leads to this formula, which just says the interfacial tension between the liquid and solid minus the interfacial tension between the air and solid plus the interfacial tension or the surface tension of the liquid air times cosine is going to equal 0. That leads to this very promising looking formula that we could calculate the actual theta, the angle of contact, based on these tensions. And that would be great if you could actually look these things up. But I tried looking these things up and they're very, very hard to find. So this is the air-solid interfacial tension. Didn't see any tables for that. Liquid-solid interfacial tension, haven't found any tables for that either. So this is not terribly practical from an engineering standpoint just because these values don't seem to be easy to find. But nonetheless, they do provide you with an understanding of what's really going on. If the air-solid tension, interfacial tension, is greater than the liquid-solid interfacial tension, that means that this term is going to end up being positive. So the cosine of theta is going to be greater than 0, right? Going to be greater than 0. So if that's positive, cosine theta is greater than 0. Cosine theta is greater than 0. These are our, remember, these are our angles. So that would be a cosine of, excuse me, that would be a cosine of greater than pi over 2. So that would be negative. So cosine greater than 0 means you've got this angle. So you've got the small angle there. So we've got the small angle, cosine of theta greater than 0. So here's my droplet. My cosine of angle theta is this, because that's going to be a greater than 0 number for cosine, less than pi over 2 in the angle. And so that's a wettable surface, leads to a wettable surface. Conversely, if the air-solid interface has less interfacial tension than the liquid-solid interface, then this is going to be negative, and you're going to have a cosine of theta that is less than 0, and that means that cosine of theta is less than 0 when theta is greater than pi over 2. So that's going to be this angle here. Remember, we're measuring theta from here, so that's going to be a bigger than pi over 2. So I'm going to get one of these droplets where I have this theta, a bigger than pi over 2 droplet. So that's going to be a droplet that is not spreading out. So that's going to be a non-wettable surface. Or if you want to call this another thing, you could call this hydrophobic. If it's water, you could call it hydrophobic. So in summary, if you have, you're looking at this, you have this drop sitting on a surface. This would be a neutral one where theta equals pi over 2 there. But in general, if theta is less than pi over 2, it's wetting. And an example of that is water on glass. So water on clean glass is a wetting surface. In fact, it spreads out very, very well. And it's also considered to be hydrophilic. And if theta is greater than pi over 2, then you've got this situation with a droplet sitting like that. That is non-wetting, and if it's water, you can say that it is hydrophobic. Okay, if theta is, this is actually low wetting, I should say, low wetting. Non-wetting is theta equals actually is equal to pi. So you have a true drop just sitting here, and theta is like this, but that's pretty rare. You have to specially engineer that. Though, actually, Professor Han-Jun Ling, who you had in thermo, he does work on super hydrophobic surfaces. So it would be interesting to know what his angles are for his droplets.